Hello friends, Mr. Burrell here. We're in the middle of Unit 9. We've been talking about solving exponential and logarithmic equations and functions. We've started talking mostly about exponential functions. We've talked about some things we can do with logarithmic functions. And now we're going to start talking about solving some basic logarithmic equations. So that's kind of what we're going to start with here. So, by the end of this lesson, these are the things that I hope that you are able to do. I hope that you're able to factor the inside argument of two logarithms and solve logarithmic equations without a calculator. So we're going to do a little bit of review on factoring. We're going to talk about solving logarithmic equations without a calculator. These ones you won't need a calculator. So, I'm going to give you some sample logarithmic and exponential functions. And what I want you to do is I want you to solve for x in each of these expressions. So, for example, I have 2 to the 5th equals 2 to the x, 5 to the 12th equals 5 to the x, etc., etc., etc. I want you to solve for x in each of the following expressions. I want you to pause this video, maybe take a minute to do that. So, notice here that on all these expressions, on both sides of the equal sign, the base of my exponential expression is the same. And on all these logarithmic expressions, the base of all my logarithms, all of the logarithms on both sides of the equal sign are the same. So, for example, if I'm looking at 2 to the 5th equals 2 to the x power, since their bases are the same, then these exponents better well also be the same. So 2 to the 5th has to be equal to 2 to the 5th. So x has to be equal to 5. Same down here. If I have log base 2 of 5 equals log base 2 of x, x better well be equal to 5. Because if I have two logarithms that are the same base, or two exponents that have the same base, the exponents, or the arguments here, we call this term sometimes an argument when we're talking about logarithms, they have to be the same. So this next example, 5 to the 12th power equals 5 to the 12th power. So x has to be equal to 12. Same here, x would have to be equal to 12. 45 to the 322nd power equals x, or 45 to the 321st power. Sorry, 321st, I said 322nd there. So if I have the same base either of the logarithm or of an exponential expression, what I'm taking the log of or the exponent, whatever function I'm looking at, they have to be the same. It doesn't make sense otherwise. Like 2 to the 5th isn't equal to 2 to the 4th. Log base of 2 of 5 is not going to be equal to log base 2 of 4. It just doesn't make sense. So the reason x is so easy to find in those cases is because if I have the same base on both sides, whether I'm looking at an exponential expression or a logarithmic expression, when I have the same base, those answers have to be equal to each other. So, let's take a look at this. I have log base 17 of negative 3x plus 1 equals log base 17 of 3x plus 7. So I have two logarithm expressions that are equal to each other. Well, notice here, I have log base 17 on the left and log base 17 on the right. If I have the same base logarithm, what I'm taking the logarithm of inside these parentheses here, they will also have to be equal to each other if both sides of the equal sign are indeed going to be the same. So I can just kind of ignore these logarithms for a bit, and I have negative 3x plus 1 equals 3x plus 7. And well, looky there, I know how to solve this equation. From here, this is just like a linear equation where I need to get x by itself. So let me go ahead, I'll add 3x on both sides, which gives me 1 equals 6x plus 7. I'll go ahead and subtract 7 on both sides, which gives me, let me write this over here, 6x equals negative 6. And if I divide by 6 on both sides, I get x equals negative 1. Negative 6 divided by 6 is negative 1. Well, let me just double check. Let me plug that back in here. Make sure indeed that I get the log of this number equals the log of this number. If I plug back in negative 1, this is negative 3 times negative 1 plus 1. 3 times negative 1 plus 7. Well, negative 3 times negative 1 is a positive 3 plus 1 is 4. 3 times negative 1 is negative 3 plus 7 is 4. So log base of 17 of 4 does indeed equals log base 17 of 4. Those are equal to each other, so I'm good. Okay? So same if I look down here at number 2, why I have two number 2s I don't know. If I have log base 17 of 7 minus 2n equals log base 17 of negative 4n plus 3, since these logs are the same, I can basically ignore them and solve with what's inside of the parentheses, or again, sometimes those are called the arguments. So 7 minus 2n equals negative 4n plus 3. Okay, let me go ahead and solve for n. I'm going to go ahead and add 4n on both sides. That will give me 2n. 7 plus 2n equals 3. I'll go ahead and subtract 7 on both sides, which gives me 2n equals negative 4. I'll write this up here so you can see it. Then to get n by itself, I'll divide by 2 on both sides. Give me n equals negative 2. So I get an answer of n equals negative 2. So if I plug negative 2 back in for n here, I get 7 minus 2 times negative 2. And on this side, I get negative 4 times negative 2 plus 3. Negative 2 times 2, or negative 2 times negative 2 is a positive 4. 7 plus 4 is 11. Negative 4 times negative 2 is positive 8, plus 3 is 11. So indeed, I get log base 17 of 11 equals log base 17 of 11, which is true. Okay, let's look at a couple other examples. So here I have log base 5 of this equals log base 5 of this. Since I have the same base logarithm on both sides, I'm only concerned with what's inside the parentheses. So negative 7n plus 1 equals n squared plus 7. So notice here, I have an n squared term. See this? I have an n squared term. So that means that this is going to be a quadratic expression. If you need a little refresher on how to factor quadratics, it might be good to watch the other video on this page. But we're going to solve this by factoring a quadratic expression. So in order to do that, I need to get everything on one side. So let's get everything on the right-hand side here. So I'll go ahead and add 7n on both sides, which gives me 1 equals n squared plus 7n plus 7. Then I'm going to minus 1 on both sides, which gives me 0. Let me write a little arrow here. 0 equals n squared plus 7n plus 6. Okay, now for the fun part. It's been a minute since we've factored a quadratic expression. So if you remember, when I'm factoring quadratic expressions, I'll look for a greatest common factor if there is one. Then I need to multiply a times c together. If this was like ax squared plus bx plus c, I need to multiply my first and last numbers together. In this case, that's 1 times 6. So I'm trying to find two numbers that multiply to make 6 and add up to 7. So can I think of two numbers that multiply to make 6 and add up to 7? Well, 1 times 6 is 6. 2 times 3 is 6. Negative 1 times negative 6 is positive 6. Negative 2 times negative 3 is positive 6. Now, which of those add up to 7? Boom. Whoops. 1 times 6 is 6. 1 plus 6 is 7. So let me come down here. In order to factor this, I'm going to write in my factors here n plus 1 and n plus 6, making sure to divide both of these terms by a, which in this case is 1. And when I divide by 1, neither of those will change, and I'll be left with n plus 1 times n plus 6 equals 0. Then to solve for n in each of those, I'm going to set each of these equal to 0. N plus 1 equals 0, n plus 6 equals 0, and then solve for n. I'm going to subtract 1 on both sides, n equals negative 1. Subtract 6 on both sides, n equals negative 6. So I have two answers, negative 1 and negative 6. Well, let's double check. Let's plug those back in, make sure I actually get the correct answer. Let me erase some of this stuff so I can see it better. So if I plug negative 1 in, that's negative 7 times negative 1 plus 1, and then negative 1 squared plus 7. Well, negative 7 times negative 1 is a positive 7, plus 1 is 8. Negative 1 squared is a positive 1, plus 7 is 8. So log base 5 of 8 is indeed equal to log base 5 of 8. If I plug in negative 6, I get negative 7 times negative 6 plus 1. Negative 6 squared plus 7. Negative 7 times negative 6 is 42, plus 1 is 43. Negative 6 times negative 6, or negative 6 squared, is 36, plus 7 is 43. So I indeed get the correct answer on both sides. Log base 5 of 43 equals log base 5 of 43. Double check my work. We're all good. Okay, let me erase some of this jazz so I can work on this second problem. So same thing applies here. I have log base 9 on the left and on the right, so I'm just concerned with what's in the parentheses here. 3v squared plus v, I'm going to ignore the logs, equals 12 plus 2v squared. This is going to be another quadratic expression, so I need to get everything on the same side. Let me go ahead and subtract 2v squared on both sides. That'll get rid of these. I'll be left with 1v squared plus v equals 12. And I'll go ahead and subtract 12 on both sides, which gives me v squared plus v minus 12 equals 0. So I need to factor this. In order to factor this, if I multiply my first and my last terms together, I need to find two numbers that multiply to make negative 12 and add up to this middle number, which is 1. So let's look at my pairs of numbers that multiply to make negative 12. 1 times negative 12, 2 times negative 6, 3 times negative 4. And then negative 1 times positive 12, negative 2 times positive 6, negative 3 times positive 4. Which of those add up to 1? This one, negative 3 plus 4 adds up to 1. So in factoring this expression, I am going to have v minus 3 over 1, v plus 4 over 1, which dividing by 1 in both of those cases doesn't change anything, and I set those equal to 0. When I set those equal to 0 and solve for v, I should get the answers of v equals 3 and negative 4. I get the answers of 3 and negative 4. And I'll let you on your own go ahead and double check those answers, plug them back in for v, make sure that I indeed get the same answer inside the parentheses on both sides. Okay, one last example I'm going to show you. This is actually an example on your homework. So what about this one? I have log base 17 of negative b plus 1 equals log base 17 of 4b minus 6. So in order to solve this, again, the logarithm bases are the same on both sides, so I can just set negative b plus 1 equal to 4b minus 6. Okay, let's go ahead and solve for b. I'm going to go ahead and add 1b on both sides, which gives me 1 equals 5b minus 6. Then I'm going to add 6 on both sides. This is kind of nice. This isn't even a quadratic. I don't even need to factor. I end up with 5b equals 7. Then when I divide by 5, I get b equals 7/5. Or if I write that as a decimal, that's like 1.2, I think. No, 1.4. 1.4. We'll take either of those. So my answer is 1.4. So if I were to plug those back in, let me double check my work here. If I were to plug 1.4 back in for b, I'd get negative 1.4 plus 1. And over here I'd get 4 times 1.4 minus 6. Negative 1.4 plus 1 is negative 0.4. And then 4 times 1.4 is 5.6 minus 6 is negative 0.4. So I indeed get log base 17 of negative 0.4 equals log base 17 of negative 0.4. Okay, all seems right in the world, right? But let me go ahead, I'm going to go ahead and double check this in my calculator here. So I've gone ahead and pulled up Desmos so you can see me typing it on Desmos. I have log base 17, I'm going to go ahead and type in negative 0.4, and look what answer I get. I get that it's undefined. Well, let me try something else. What if I did like log base 17 of positive 0.4? Well, that gives me an answer. Why on earth do I not get, why is this undefined? Why do I get, when I take the log of this negative number, why is that undefined? So I'm going to come back to this slide in a minute. Let's go ahead and I'm going to go over to this slide real quick. Why can't I take the log of a negative number? So if you reflect back to when we were talking about the graphs of logarithmic functions, note that this was the graph of my log function. If I have log of x, I crossed the x-axis here at 1. I had a vertical asymptote at 0, which meant my domain was from 0 to infinity. Let me say that again. The domain, or all the possible x values, are from 0 to infinity, meaning that any x value less than 0, any value that I plug into this log function less than 0, isn't going to work, because the domain of a logarithm function is only from 0 to infinity. Those are the only input or x values that will work in a log function. So if I go back here, having the log of a negative number, that's less than 0, that's not going to work. That answer is undefined, or I'd say no solution. So this solution that I got, since when I put it back into the logarithm, it forces me to take the log of a negative number, this is going to be no solution, or undefined is a way that you could write that like it did in Desmos, but a question like that would be no solution. Okay, why can't I take the log of a negative number? We just determined that. So, hopefully now you feel a little bit more comfortable solving expressions like that. Really, today was a review of how to solve quadratic functions and linear functions. So hopefully you are now able to factor the inside of two different logarithms and solve logarithm equations without a calculator, remembering to double check your work for the term that we've used in the past for solutions that don't work when you plug them back in are extraneous solutions. So hopefully you now know how to check for those extraneous solutions, or the solutions that when we plug them back into the logarithm make me take the log of a negative number. I hope that was helpful. Please reach out to me if you have any questions whatsoever, and I hope that you enjoyed that as much as I did.